Introduction. Acids and bases are fundamental to chemistry, influencing a myriad of processes in our everyday lives. They react with each other and various substances to create a vast array of chemical reactions. Let's explore the different theories that have shaped our understanding of these dynamic entities. Section 1. Arrhenius concept. Our journey begins with the Arrhenius theory proposed by Svante Arrhenius. According to this concept, acids are substances that produce hydrogen ions H+ when dissolved in water, while bases produce hydroxide ions, O. 1. A classic example is hydrochloric acid, HCl, and sodium hydroxide, NaO, which readily dissociate in water to form ions. 2. Arrhenius concept. 3. Hydrochloric acid, HCl. 4. Sulfuric acid, H2SO4. 5. Nitric acid, HNO3. 6. Acetic acid, CHICU. 7. Hydrobromic acid, HBr. 8. Hydroiodic acid, HI. 9. Carbonic acid, H2CO3. 10. Phosphoric acid, H3PO4. 11. Citric acid, found in citrus fruits. 12. Formic acid, CU. 13. Benzoic acid, C6H5CU. 14. Hydrofluoric acid, HF. 15. Hydrocyanic acid, HCN. Tartaric acid, found in grapes. 1. Oxalic acid, H2C2O4. 2. Arrhenius bases. 3. Sodium hydroxide, NaO. 4. Potassium hydroxide, KOH. 5. Calcium hydroxide, CaO2. 6. Ammonium hydroxide, NH4O. 7. Magnesium hydroxide, MgO2. 8. Aluminum hydroxide, AlO3. 9. Barium hydroxide, BaO2. 10. Sodium bicarbonate, NaCO3. 11. Sodium carbonate, Na2CO3. 12. Sodium silicate, Na2CO3. 13. Potassium carbonate, K2CO3. 14. Ammonia, NH3, weak base. 15. Ethylamine, C2H5NH2, weak base. Diethylamine, C4H11N, weak base. Aniline, C6H5NH2, weak base. Section 2. Bronsted-Lowry concept. Moving forward, we encounter the Bronsted-Lowry theory. This theory expands the concept of acids and bases beyond aqueous solutions. In this view, an acid is a substance that donates a proton, H+, while a base is a substance that accepts a proton. Ammonia, NH3, acting as a base by accepting a proton from water is a prime example. Examples of Bronsted-Lowry acids are hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3, acetic acid, CHICU, hydrogen sulfide, H2S. Examples Bronsted-Lowry bases are ammonia, NH3, hydroxide ion, O, amines, such as methylamine, CH3NH2, ethylamine, C2H5NH2, and aniline, C6H5NH2. Carbonate ion, CO3-2. Section 3. Lewis concept. The Lewis theory, proposed by Gilbert and Lewis, delves into electron pairs. In this perspective, an acid is an electron pair acceptor, while a base is an electron pair donor. This broader concept allows us to understand reactions that involve coordination compounds and other non-aqueous systems. Examples of Lewis acids: boron trifluoride, BF3, aluminum chloride, AlCl3, iron 3 chloride, FeCl3, zinc chloride, ZnCl2, hydrogen iodide, Hi, magnesium ion, Mg²+, tin 4 chloride, SnCl4, silver ion, Ag+. Examples of Lewis bases: ammonia, NH3, water, H2O, hydroxide ion, O. Amines. Phosphine, pH 3. Thiourea, CSNH22. Cyanide ion, Cn. Alkoxide ion, Rho. Fluoride ion, F. Section 4, Lux-Flood concept. According to this concept, a base is any substance which gives up oxide ions and an acid is any substance which gains oxide ions. That is, acids are the oxide ion acceptors, while bases are the oxide ion donors. 1. Examples are sulfate ions, calcium oxide are base while CO2 is acid. 2. Section 5, Usanovich concept. 3. Continuing our exploration, we encounter the Usanovich concept, proposed by Lowry Usanovich. 4. This theory suggests that acids and bases are electron pair and electron deficient species, respectively. 5. It is the extension of Lewis' concept. According to this concept, an acid is any chemical species which reacts with bases, gives up cation or accepts anions or electrons, and a base is any chemical species which reacts with acids, gives up anions, or accepts cations, or donates electrons. 1. Cl2, acid, plus 2K, bases, 2KCl, salt. 2. SO3, acid, plus Ca, base, CaSO4, salt. 3. Section 6, General Trends in Acidic and Basic Properties. 4. As we've journeyed through various theories, it's crucial to understand the general trends in the properties of acids and bases. 5. Across the periodic table, elements on the left tend to exhibit acidic behavior, while those on the right exhibit basic behavior. For example, hydrogen chloride, HCl, is a strong acid, while sodium hydroxide, NaO, is a strong base. Trends in acidic properties. Periodic trend. Acidity generally increases across a period, from left to right, in the periodic table. This is because elements to the right have higher electronegativity, making it easier for them to hold on to their electrons and release protons as acids. Atomic size. Acidity increases down a group, vertically in the periodic table. Larger atoms have weaker hold on their outermost electrons, leading to easier release of protons and increased acidity. Oxidation state. For elements in the same group, as oxidation state increases, acidity tends to increase. This is because elements with higher positive charges on their central atom can more readily release protons. Resonance and inductive effects. Molecules with more stable resonance structures or greater electron withdrawing inductive effects tend to be more acidic. Elemental properties. Nonmetals tend to form more acidic compounds when combined with hydrogen, especially if they can stabilize the negative charge that results from the released proton. Trends in basic properties. Periodic trend. Basicity generally increases down a group in the periodic table. Larger atoms have more electron density and can more easily donate electrons, exhibiting stronger basic behavior. Atomic size. Basicity decreases across a period in the periodic table. Smaller atoms can hold on to their lone pair electrons more tightly, making them less likely to donate electrons and act as bases. Electronegativity. Elements with lower electronegativity tend to be better donors of electrons, leading to stronger basic behavior. Hybridization. Inorganic compounds, sp³ hybridized nitrogen atoms are generally more basic compared to sp² or sp hybridized nitrogen atoms. Resonance effects. Molecules with stable resonance structures that involve the donation of lone pair electrons are generally more basic. Conclusion. Acids and bases aren't just confined to the laboratory, they're present in every corner of our lives. From the tangy zest of a lemon to the soothing suds of a soap, the effects of these substances are all around us. They influence the taste of our food, the cleanliness of our homes, and the very chemistry of our bodies.